Greetings. A very important extension of our study of gas mixtures is when you have a mixture of air and steam or water vapor. The reason is that it directly concerns human comfort. You see, there are three important aspects to our comfort. First is temperature, then it is the humidity, and the third is the velocity of the air surrounding us. And so humidity is basically how much water vapor is mixed with the air, or how much water vapor we have inside the air that we live in. Usually, a number about 60% humidity is good for our living and for our comfort. But quite often, in a humid environment, like what we would see in seaside, you would have humidities as high as 99%, or in cold climates, we would have humidities as low as perhaps 10%. So we study this subject within the structure of our usual study of thermodynamic problems. It would tell us how we calculate properties of a mixture of air and steam, and also what would the correct diagram be that we could represent and draw our problem on it. So the climate that we have in this example is air at is air, and usually it's denoted with its temperature, which is 27 degrees C. Let's call it dry bulb temperature, since it's the temperature that we measure with a thermometer. And also its humidity, which is phi equals 50%. This is the incoming air, and the outgoing air that we wish to have, we also denote it with its temperature, and the temperature is 10 degrees C, and its humidity is 90%. And what happens to cool this air is that you have a coolant coil that goes into this air, cools it down, and also it also gets some condensate out. So some of the water inside the air could condensate and come out. Now, the problem tells us that we have a room which we have an enclosure where the volume flow rate is 10 cubic meters per minute. So what should happen is that we should have 10 cubic meters per minute of flow inside this instrument, which provides for us the type of air that we want. Now, this could be a room of 10 cubic meters volume, or an enclosure of 10 cubic meters volume, and it is said that we want this air to be changed once per minute. This is the definition of the problem, and just like every problem, the humidity problem or air conditioning problems, we shall follow 5 steps. And I would repeat those steps for you as I have done. It is to decide on the boundary. Second, calculate properties. Or read them from a box or from a table or however you do it. Still collect the properties. 3, draw a diagram. 4, simplify the governing equations. And finally, 5, get everything together to solve the problems. Solve the problem for what is asked. And that is what we do. But for air conditioning problems, as we are concerned with them now, 2 things are important first. First, how to calculate properties of a mixture of air and water vapor. That's the first important thing. Second, which one is the correct diagram? Which diagram would better represent our problem? And that's where we learn what the psychometric chart is. And then how do we simplify our governing equations, since now we have equations for 2 substances, one for air and for water vapor, but we have a mixture of them, and how do we consider them both? So we have to handle these questions, and the first question that I want to discuss is how to calculate properties. Well, as before, I draw a table for the properties that is of concern to us. Now, the 2 properties that we are usually given are temperature and humidity. And in this case, for point 1, our temperature is 27 degrees C and our humidity is 50%. In the final condition, which is case 2, our temperature is 10 degrees C and our humidity is 90%. In a real air conditioning problem, there could be plenty of different 2 or 3 different air conditioning processes. And I hope that in my future videos, I would be able to solve problems of different air conditioning problems, but they would all be very, very similar to this one. The next property that you could easily calculate is the saturation pressure of water at this temperature. So what we do is just to go to the tables and use this temperature to see what saturated pressure of water at these 2 temperatures are, and what we would gain from that is that for 27 degrees C, the saturation pressure would be 3.567 kilopascal, and for case 2, it would be 1.228 kilopascal. It doesn't mean that this is our partial pressure of water vapor. It just means that what would the partial pressure of water vapor be if it was saturated in the mixture, if it was saturated in this temperature. It doesn't mean that the partial pressure of our present water vapor in point 1 and point 2 is anything like this one. In fact, we shall calculate those partial pressures shortly. The other reading we may have from the table is the enthalpy of saturated water vapor. And in the case of 27 degrees, it is 2550.8 kilojoule per kilogram, and in the second case, it is 2519.8 kilojoule per kilogram. So with 10 degrees C, we go to table and Hg is this value. With 27 degrees C, we go to table, Hg is this value, and also the saturation pressures are also written here. Now, the next step for us is to calculate what the partial pressure of water vapor is inside our very mixtures. So in this case, PV equals 50%, that is 0.5 times the partial pressure if water was saturated in the mixture. And if water was saturated in this mixture, its partial pressure would have been 3.567. And therefore, PV here is 1.7835 kilopascal, which I would write it here, 1.7835. And the second case, PV1, let's call it, and PV2 would be 0.9 times the partial pressure, the saturation pressure at that temperature, which is 1.228, and that would be 1.1052 kilopascal. And I would just write it here as well, 1.1052 kilopascal. You see, we have used one very key equation, which tells us that P equals PV over PG. It means that you just read partial pressure of the saturated vapor at the temperature of the mixture you have. And this is PV, which is the partial pressure of the real vapor. This is the saturation pressure, and this is the partial pressure of the water vapor you actually have in your mixture. And to calculate that partial pressure, it's easy. You could just multiply V by PG. And this is the outcome we get here. Now, We have two properties, and we need to know what W, M dot A, or M dot V are. For W, we have this equation that W equals 0.622 times PV. So for case 1, it is 1.7835 and divided by P, which let's assume it to be 100 kilopascals minus 1.7835. And the outcome for W1 is 0.0113, 0.0113, and the unit of it is kilogram vapor per every kilogram of dry air. So what we do here is we just write it down here, which should be 0.0113, and the unit is kilogram of vapor per every kilogram of dry air. Repeat this practice for W2, and for W2 it would be 0.622 times PV2, which is 1.1052, and divided by 100 minus 1.1052. And the outcome for it is 0.00695, and the unit is just as above. And I could just write it down here to complete this table, 0.00695. And this is the um, specific humidity of um, the specific humidity of the mixture that we have. This is the mixture that we have, and now we have specific humidities for condition 1 and also for condition 2. Well, the next step in our calculation is to calculate the mass of air, that mass of dry air that is going through the process. And this is the next column in our table. So what we need to calculate the mass of air, of course, volume is the same for air, for vapor, and for the mixture. That's how we assume it. We need partial pressure of air, which is the total pressure minus vapor pressure. Temperature is the same for both, and also R for air is known. So the way we calculate it is to say that partial pressure PA for case 1, for the initial case, is 100 minus 1.7835, and that equals 98.2165 kilopascal. Once we know the air partial pressure, then we also know that V dot is 10 cubic meters per minute. This is what we were given from the problem. So PA1 is this value, and V dot is 10 cubic meters per minute, which is equivalent of 0.17 cubic meters per second. And therefore, just use this equation. M dot for A is, of course, we calculated at station 1, but that would be the same for both stations. M dot is PA, which is 98.2165, as we just calculated it, times V dot, which is 0.17, and divided by 0.287, which is R for air, and its temperature is times the inlet air is 27 degrees, and that would be 300 Kelvin, and that equals 0.194 kilograms per second. 0.194 kilograms per second. So we could just write it down here, 0.194, and shortly we shall see that it's the same at exit. But let's just, although it's very obvious to us, but that's what the mass balance will later on tell us. Now, vapor, the mass flow rate for vapor is just W multiplied by M dot A. So it's easy to calculate vapor mass flow rate as well. And it would be vapor mass flow rate, M dot V, equals W, which we have just calculated, 0.0113 times the mass flow rate for air, 0.194, and the outcome is 0.00212, say 2, with very good approximation. I have calculated here 0.0022 kilograms per second. And the final thing we would need is enthalpy of the mixture. We could have a value for the mixture enthalpy, and that's what we just do now. The value for mixture enthalpy is H is HA plus W HG. And that's very simple to calculate. I would just do it here. HA, H equals HA, which is CP0TA, since it's air and it's perfect gas. So we could just do it plus the enthalpy of the water vapor, which is WHG, and that's why we read HG from the tables. Start with when we just we had the temperature, we were reading the saturation pressure, and therefore we just read the saturation enthalpy for the water vapor, and we can use it here. So H1 equals Cp0, which say 1.005 times T, which is 300 degrees, 300 Kelvin, plus 0.0113 and times Hg, which is 2550, and the outcome is 330.3 kilojoule per kilogram of dry air. Don't forget that it's per kilogram of dry air. A very common practice in air conditioning is that they sometimes ignore the value for Kelvin because you would always have a delta H, and that 273.15 would disappear from both uh, H1 and H2. So what they do, and you see it in some books, is that they put just that 27 here, and instead of coming to 330, they would come to 55.96, 55.96 here. And for H2, we could calculate it to be 1.005 times 283 plus 0.00695 times 2519.8, and the outcome is 301.9 kilojoule per kilogram dry air. And if we had used a value of 10, this would have been 27.56, which of course the difference would be the same. In some air conditioning problems, they don't use any of them, they don't use either of them. But what they do is that they assume their base temperature to be minus 20 degrees C. Since most air conditioning problems are concerned with the temperature range from minus 20 degrees C to, say, 50 degrees C. So they place the base on minus 20 degrees C and then do all calculations in that range. So all values would be positive and they wouldn't have a negative value. It's not the point in this problem, but that's what is sometimes done. Okay. So let's move these values to our table, and we will have a 330.3 here and 301.9 here, kilojoules per kilogram of air, which is in fact the enthalpies of incoming and outgoing flows as compared to 1 kilogram of dry air. Uh, since these calculations are pretty standard and simple to calculate, they are usually done and um, expressed on a psychometric chart. This is a psychometric chart, and as you know, the horizontal axis is the dry bulb temperature. It's in fact, the temperature that we just were talking about. And these green lines are the humidities. So 10%, 20%, 30%, and go anywhere up to the 100%, which is the final green line. These are humidities. And since we can calculate the other values just like we did, here we also can uh, present them and know that for a specific temperature and humidity, we could read a specific humidity W from this vertical axis. And we could do it for our problem, and we would just shortly do it. These are all values for enthalpies, and as you see, they have assumed 0 centigrade as their base for enthalpies and put different values for enthalpies of the mixture per kilogram of dry air on this line. So what we do is to put our problem on this diagram. And this is how it would look like if we draw our problem on a psychometric chart. You see, point 1 has 27 degrees centigrade, this is 20, this is 30, and this is 50% humidity. And point 2 is 10 degrees centigrade and is 90% humidity. Our process is from point 1 to 2. And we could also read values of specific humidity from here and also from here, I mean from the vertical axis, we could read values of a specific humidity, and they would be very, very similar to what we have already calculated. We could also read values for uh, enthalpies from these two lines and from this point and from this point. So if we just use this psychometric chart, we could we could place different points of our problem or our different problems on this chart, draw our processes, and also calculate enthalpies and specific humidities for different points and bypass, in fact, those calculations. All the same, this would give very good approximations, but if we need exact values, we could do the calculations, which are not that difficult. Our next step is to simplify our equations, and we usually need first two equations, which is the mass conservation and the energy equation. We could, in fact, we shall use mass conservation for both components independently, but the enthalpy of the mixture is also possible to calculate. And so what we would need in our calculations are two equations for mass conservation and a single equation for energy equation. Problem is steady state, so the left-hand side usually vanishes, and therefore we have incoming and outgoing mass. Usually work has negligible effect, and therefore heat is calculated from the difference between incoming and outgoing entropies. Changes in the velocity and elevation are also negligible. So what we do here is to write down the mass conservation equation, which for air, it would be 0 equals m dot A1 minus m dot A2. And this is the mi, this is m sub e, and therefore what we conclude from this equation is that m dot A1 equals m dot A2, and that equals m dot A. Of course, it is pretty evident at this stage for every student, but I would just insist to use this equation and make it a conclusion, just to make sure that we all remember the old process of drawing such conclusions that incoming mass and outgoing mass are equal, just drawing such conclusion from our equation and from the mass conservation law. So if m dot A is the same, this would be 0.194. And since we have W, we could multiply it by 0.194 and calculate the mass flow rate of the vapor. And the vapor mass flow rate here would be just the product of these two values, and I will just write it here. W2 equals 0.00695 times 0.194. Air mass flow rate doesn't change, and that equals 0.0013483 kilograms of vapor. 0.0013483. And here we have all the properties that we need for points 1 and 2. Continue our equation for water flow, and it's a continuous equation. So for water, for vapor, 0 equals m dot of vapor at entry minus m dot vapor at exit, and minus, there would be some water out because they're not equal. Some water condensates. So m dot water that condensates. If in some air conditioning process we spray water into air, which we do sometimes, then this would be a plus. This would add to the incoming water mass flow rate, vapor mass flow rate. Now here we expect some vapor to condensate and then go out, and therefore this would get a negative sign. Anyway, we usually write down these values as a portion of air mass flow rate. So this would be 0 equals, instead of the vapor mass flow rate, we write W1 times m dot A minus W2 times, again, m dot A minus m dot W. Or simply 0 equals m dot A times W1 minus W2 and minus m dot W. So, although here, just for clarification, we calculated m dot V, and in fact, we don't need it, we don't use it. It's not a common practice in air conditioning cases to use the vapor mass flow rate, and we just use W times m dot A. That's the common practice in air conditioning calculations. And here we just can calculate that m dot W, which is the mass of extracted water, the so-called condensate is the water that goes out from a different point. It drops out, and its mass is equals m dot A, which is 0.194, and times W1, which is 0.0113, minus W2, which is 0.00695, and to a good approximation, it is 0.0007776 kilogram per second. You see, although it looks negligible if you calculate it per second, but remember, if you calculate it in an hour, you have to multiply it by 3600. If you calculate it in a day, then it would be 24 hours a day, and the number then would be an important mass of water that is being drift out, in fact. So the energy conservation, for energy conservation, well, it's continuous flow, it is a steady state flow. So the left hand side would be 0, and the right hand side would be m dot times h1 minus m dot times h2 and minus m dot water times h water. This is the incoming flow, this is the outgoing flow, plus q dot, which is the heat transfer. This is the equation that we could write for the energy conservation. Please remember that we need to put mass of air here. This is mass of water, which is the water condensate going out. But here we need to put mass of air, since this is the enthalpy per unit mass of air, and once it's multiplied by the air mass liquid, then it would produce the total enthalpy of water vapor plus air in the mixture. So this would equal 0.194 times 330.3 minus 0.194 times 301.9 minus 0. mass of the water condensate, which is 0.000776 times 42.022. Where did we get this value? This is the value of the condensate. The temperature of the condensate would equal T2, and we just went to the tables, used the tables, and read this value for saturated liquid water. X equals 0, and plus Q dot, and the outcome for Q dot would be minus 5.477 kilowatt. We could also move to calculate the second law and also availability equation. We don't usually do it for teaching air conditioning processes, but if it's required, there is nothing new to it, and you could do it as well. Well, thanks very much for watching this video, and cheers.